All right, so as I was saying, so the first 2 points are basically why we need an ADC. So that was the first 2 points, and we know that for an ADC we also need a transducer. Now we directly go to the different points of an ADC. The first thing is that an ADC has n bit resolution. For the time being, let's leave it like that. Let's just know that ADC has n bit resolution where n can be 8, 12, 10, 16, I mean all these numbers, okay? It can be any resolution. So let us know up to this for the time being. Just in the next page, you will understand the significance of this resolution and the relation with these bits. Moving on, if anyone need time to write, you must stop me. Otherwise, I'll just keep on going. Okay. All right, so in the last page, we finished up to resolution. So now we see that a higher resolution provides smaller step size. So from this point, we get the significance of resolution. So if my resolution is high, my step size will be smaller. And if my resolution is low, my step size will be larger. So now we need to know what is the step size to create a complete sense of all these things. So finally, we see that step size is the smallest change that can be distinguished by an ADC. That means smaller the change or smaller the step size, better is our ADC. So in order to get smaller step size, what do we need? We need higher resolution. So how can we get higher resolution? By increasing the number of n bit in resolution. So if we have two ADC, say one of the ADC is 8-bit ADC and another is 16-bit ADC, and if we want to find out which one is more efficient, definitely the answer will be 16-bit ADC, because it can detect change in a much smaller magnitude in comparison to the 8-bit ADC. We will see more examples related to this step size and resolution in a little bit. So have patience. And the last thing we have, not the last thing, second last thing is that conversion time. So this is the time that your ADC takes to convert your analog signal to a digital number. One thing to remember is whenever we say digital in this chapter, we mean binary, okay? So we take an analog signal or analog input and we convert that into a binary number. And finally, an ADC can be serial or parallel. In parallel, normally we have 8-bit or more lines. I mean output or input or data lines, whatever you say. But in serial, we have only one output line. So that's it about the introductory discussion about ADC. Okay, so let us now see the table which is related to resolution and step size. This table is there in your book. If you don't want to write, you can avoid it, no problem with that. This is your table 13.1. The table. So we will take a few examples because if you just understand one example, it will be very easy to understand the rest. All right. So if the resolution is 8-bit, that is the value of n is 8, then to find the number of steps, we use the formula 2 to the power n. So if we write 2 to the power 8 in this specific case, we will end up getting 256. So this is the number of steps. Now, if we want to find the step size, look at the unit, it is in millivolt. So for finding, we write 5 divided by the number of steps, and it will give us 19.53 millivolt. Now let us increase the resolution to say 10-bit. So apply the same thing. 2 to the power n will give us 1024. The next process is still same, 5 divided by 1024, and you will see that now this is capable of detecting change to as low as 4.88 millivolt. Similarly, if we keep on increasing to 12 or 16, which is there in your book, we can see that finally you will get over here 4096 and 65536. And the value of its step size will be 1.2, and this one will be very small, that is 0.076. Okay. Now, there should be one question. The first column and second column is pretty straightforward to understand. In the third column, the denominator is understood, but why are we using 5 as the numerator? Okay, so that is the question. The answer over here is we have connected the VCC to 5 volt, and this works as our reference voltage. However, this is not always the case. Okay, the reference voltage can be changed. So whatever is our reference voltage will be the numerator in determining the step size. So when can a reference voltage change, you will understand in a little bit. For the timing, just know that VCC is connected to 5 volt, and this 5 volt is the reference voltage in this scenario. That's why the numerator in finding the step size is 5. Okay. All right, so let me pause over here. If any one of you have any question up to this, please ask. All right, if there is no question, let me move forward. At least you guys are hearing me, right?
Yes, sir.
Yes, sir.
Okay. Now let us study our specific ADC. Okay, this is ADC 0804 chip. Alright, so this is the introduction of your ADC 0804 chip. It is an 8-bit parallel ADC. The resolution is 8-bit. It works with +5 volt, and the fastest conversion time can be 110 microsecond. It cannot be more than this. And it depends on the clocking signal applied to clocking. Very simple. Please go through this figure, okay? Figure 13.1. I'm not drawing this figure. This is the figure of your ADC 0804 chip, where all your pins and various connections are given. So go through that figure, and you will need that figure to understand the pin description and rest of the things. So I'm not drawing the figure, it is there in your book. So I mean, see whenever you get time and correlate with whatever I'll be writing next, okay? Correlate with the figure. Now let us see the pin description. So we begin with chip select, which is an active low input. The meaning of active low is that whenever this particular pin is low, the corresponding chip will be activated. Okay, this is the significance of an active low input. So this one is used to activate the chip. The next one is read, RD. It can be referred as output enable. When CS is equal to 0, very obvious, CS has to be 0 in order for the chip to be activated. So whenever CS is 0 and a high to low pulse is applied to the RD pin, then the 8-bit output will show up at D0 to D7 data pins. And you can see that all these pins are connected to your LED. So simply we signify that the conversion is done. I mean, the data is ready to be displayed. That is what we mean by this RD pin. So wherever CS is equal to 0 and a high to low pulse is applied, we specify that the data is ready to be read. So the data shows up at D0 to D7 data pins. So now how you connect this D0 to D7 is totally up to the user or the coder. But this is, I mean, the RD signifies that the data is ready to be read. Now, WR is also known as write or start conversion. The first and foremost thing, CS has to be 0. And now if a low to high pulse is applied in the WR, then your ADC will start the conversion process. After the conversion is done, this is another pin which is INTR. It becomes low. Okay, let me repeat again. So whenever INTR pin is low, we understand that the conversion by the ADC 0804 has completed. Okay, so that is the purpose of our INTR pin. Moving on.
So there's a separate V in and read port to the ADC.
There is a separate V in and VCC.
Uh, there is separate V in and RD. D0 to
Yeah.
D. So we can feed data to the ADC through the RD port.
No, the data is not fed through the RD port. The RD port is only used to specify whether the data is ready to be displayed or not. The data is not fed through the RD pin. Was that your question?
Yes, sir.
Data is not fed through the RD pin. Okay, RD pin is for a different purpose.
Entire pin to know if the conversion is done. So why the RD pin is needed?
Oh, okay. This INTR is for each and every conversion. You do not display the data after each and every conversion, right? You accumulate some data to be displayed. See, the data that you will display will be 8-bit data. Okay, and the conversion, the INTR signifies after each and every conversion. So these two actually differs. You display the data maybe after a specific period of time or something like that. So displaying data and completion of this conversion are two different things. They are not the same thing. Okay.
Okay, sir.
So now let us see clock in and clock out. So if we want to use the external clock, then clock input should be connected to the external clock. But if you want to use the internal clock, then these two should be connected to a capacitor and a resistor, which is there in your figure 13.1. Normally the value of the resistor is 10 kilo ohm and capacitor is 150 picofarad. And this is the formula for finding the frequency. If you give these two inputs in this formula, you'll see that the frequency is 606 kilohertz for this particular combination. Now, interrupt pin is already discussed. It is normally high and it will go low to specify that the conversion is over. Then we have V input positive and V input negative. The formula is V input is equal to V in plus minus V in negative. Often this one is grounded, so V in positive acts as our analog input. And finally, we have the VCC, which is the plus 5 volt power supply. We told you this is the reference voltage only when this particular pin, you will see in the figure that there is a pin which is known as Vref by 2. So if this pin is not connected, then only VCC will act as the reference voltage. But if this pin is connected, then the reference voltage will be different, as we will see in a while. All right, so these are the pin configurations. We are only left with Vref by 2. So now let us see Vref by 2. So this is the Vref by 2, which is used if our input voltage is any voltage other than 0 to 5 volt. And an example is also given. So based on that example, let us complete table 13.2 and the rest of the things will be very clear to you. So please try to help me, okay? If our V input is 0 to 5 volt, then what will be the voltage which is to be connected to Vref by 2? Can anyone say? The question is, if V in is 0 to 5 volt, to what voltage will Vref by 2 be connected?
Nothing.
Exactly, it will be open because this is the condition. This is given in the description of Vref by 2. In that case, our step size will be input voltage 5 divided by 256, which will remain the same as we have seen earlier, that is 19.53. Now, if the range is 0 to 4 volt, I should not write volt over here because it is already given at the top. Okay. Now tell me, if it is 0 to 4 volt, then Vref by 2 should be connected to which voltage? It is also given in the description as an example. So it is very obvious. Anyone? Your Vref by 2 should be connected to which voltage?
The 2 volt.
Yeah, very obvious, 2 volt. Anyway, so the step size will now be changed. Okay. Now your reference voltage will be twice of the Vref. So now the step size will be 4 divided by 256. That is 15.62. Okay, I think the connection was a bit unstable. I'm repeating. If Vref by 2 is connected to 2, then determining the size voltage will be twice of that Vref by 2, which gives us 4. So now the step size will be 15.62. Similarly, if we go from 0 to 3, your Vref will be connected to 1.5 volt. So the step size will be 3 divided by 256, and it will be 11.71. Finally, if the range is from 0 to 2.56 volt, then your Vref will be connected to 1.28, and 1.28 divided by 256 will give you 10. Now this is very obvious. The only simple question is, why is the denominator 256 every time? This is also very obvious because this is an 8-bit resolution ADC. So that's why the denominator is always 256. But the numerator is my reference voltage, which may change based on the connections or ranges. The last pin we have are D0 to D7. These are the digital output pins, which may be connected to any device according to the user. The only thing to remember is that the D7 is your MSB, while D0 is your LSB. And that's the end of your pin description of ADC 0804 chip. So if anyone has any question, you can ask.
What happened to Vref at this point if we are using Vref by 2?
What is the
Use of V reference pin.
V reference pin or V reference by 2? Which pin? There is no V reference pin.
Vref pin. There was a Vref pin.
I don't think there is any VREF pin. There is VREF by 2, but there is no pin as VREF.
So you told something about Vref in the previous slide.
Yeah. In this slide, I said that VCC will act as the reference voltage. Is this what you are asking?
Yes, sir.
So this is different case. This is VCC. So if VREF is only, VREF will be your reference voltage. VREF by 2.
Okay, sir.
Anyone else? Any other question? Okay, so if you do not have any question, let me stop sharing. You're gonna stop the recording process. Let me just take your attendance.